Hi everyone, this is Mrs. J, and today we're going to talk about probability distribution and normal distribution. Alright, so first I have a quick warm-up for you guys, so please pause the video and see if you can complete this chart and then make a histogram of the data. Alright, go ahead and check your work here. So remember, for these, the total number of outcomes, the denominator is 2 to the power of 5, because for each flip there's two options, heads or tails, with an equal probability. So it's just fundamental counting principle for that. And then if you're considering heads to be a success, and again you have 5 flips, how many ways can you take 5 flips and get 0 heads, or 1, or 2, or 3, or 4, or 5. So remember, for this, I know that we're flipping a coin, the same coin, multiple times, but it really doesn't matter the order that these are happening. We just need to know which flip is achieving the head. So that's why it's a combination. All right, and then if you look at what a histogram of these results would be, where your x-axis is the number of heads and the y-axis represents the probability of that occurring, you could see that we actually have this normal distribution. So you'll see things like that when we have an experiment with 2 options where each option is equally as likely to happen, just like flipping a normal coin. Now, when we were doing previous coin flip experiments, like in the warm-up, we're assuming again that it's a fair coin, like a normal quarter, so you have an equal chance of getting heads or tails. But today we're going to talk about, well, what can we do if we don't have that equal chance, but there's only 2 options in an experiment? So here we're going to look at theoretical probability distribution. So first, a binomial experiment is an experiment where there's only 2 outcomes, so a success or failure, like flipping a coin. Now, again, most coins, it's, 50-50 chance of whether you flip a heads or tails. But again, to address cases where it's not, we can use this. So the probability of, if P is the probability of success, sorry, I shouldn't have written of twice. So if P is the probability of a success and Q is the probability of failure, so just by definition, 1 minus P should equal Q. The successes and failures should add up to 1. The binomial probability of R successes from N trials can be found using this formula. So we do N choose R, and then we do P to the power of R. So remember, P is the probability of getting a success to the power of R, and then Q to the power of N minus R. So the number that are not successes. N minus R is just, again, the number of failures, essentially. So we can use this when we have something that the probability of each outcome is not the same. It also works if it is the same, but you don't really need to consider this because it will really cancel each other out. Okay, so let's try this example. Here we are doing this binomial experiment of flipping a trick coin 5 times, and we're considering getting a heads to be a success. So this trick coin lands on heads 75% of the time. So the probability of getting a success, which is a heads, is 0.75, which means the probability of a failure is 0.25. So again, we only have these 2 options, heads or tails, but because it's a trick coin, the probability of one is not equal to the probability of the other. So we want to find the theoretical probability for this trick coin of getting 0, 1, 2, 3, 4, or 5 heads. So we'll use that formula that we just learned about. So for 0, we'll do 5, choose 0, because again, heads is considered to be a success. And then we'll do P, which is 75%, or we could even say 3/4 to the power of 0. And then 1/4 to the power of 5. So remember, this is how many successes, and this is essentially how many failures. So in this case, there's 0 heads, so there's 0 successes and 5 failures. Then if you plug this in and simplify the fraction, you get 1 over 1,024. Now for the next one, for the probability of flipping a 1, we would do 5, choose 1. So 5 flips, 1 favorable outcome. So then you do 3/4 to the power of 1, which means that the other one for failures, there are 4 failures, so which is just 5 minus 1. So then you can plug this in and simplify, and you get 15 over 1,024. For the theoretical probability for 2 heads, 5, choose 2 times 3/4 to the power of 2 times 1/4 cubed. So again, here there's 2 successes and 3 failures. And here we should get 90 over 1024. For 3 heads, we have 5 choose 3 times 3/4 cubed times 1/4 squared, which ends up being 270 over 1024. Then for 4 heads, 5 choose 4 times 3/4. So there's 4 successes and 1 failure, which gives us 405 over 1024. And then again, all of them are successes. So 5 choose 5 times 3/4 to the power of 5 and 1/4 to the power of 0. So that would be 243 over 1024. So now you'll notice that unlike in the warm-up, you know, the results here are not symmetrical. It's not the same coming from left or right, and because the probability that you get a success is different than the probability that you get a failure. So this nice formula helps us find the theoretical probability of a binomial experiment where the 2 options have different probabilities of occurring. And now for this one, if you look at a histogram of your results here, unlike in the warm-up, you can see that our distribution is actually skewed left. So we see that a lot of our data kind of seems to be clumped to the right. So because of that unequal probability, we see that we no longer have that normal distribution. All right, so I have one for you to try on your own. So go ahead and pause the video and give it a shot. All right, go ahead and check your work here. So again, this time the probability of a success is 0.4, 40%, so 2/5, and so the probability of a failure must be 3/5. So you can see here I have the formula filled out and I have the reduced fractions here. If you kind of turn these values into a histogram, you'll see that our, again, the distribution of our data is kind of skewed. So this time it's skewed right. And again, that's because the probabilities are not the same for both heads or tails. However, you could see that it's a little bit closer to looking like a normal distribution than the last example, and that's because the probabilities of heads or tails is a little bit closer than the last example as well. So now we're going to focus our attention on what's called a normal distribution and how we can interpret data that follows a normal distribution. So all normal curves, if we consider something to be normally distributed, it has these properties. So here you can see in the middle we have our mean, and then here you can see that we're adding or subtracting multiples of sigma, which remember is our standard deviation. So if you go 1 standard deviation to the right or left, that will always encompass 68% of your data. So 34% to the right, 34% to the left. And so that's for all data that follows a normal distribution. And then between the first and second standard deviation away, that's an extra 13.5% on either side. So this area is 13.5, this area is 13.5. So if you add up all 4 of those, you get 95%. So 95% of your data is going to be within 2 standard deviations of your mean, which means 2 to the right or left. And then you can see in this third column to the right or left is an additional 2.35, 2.35. So if you add that, from here to here, it encompasses 99.7% of our data. So essentially all of our data, almost all of our data, is going to be within 3 standard deviations to the right or left of our mean. So again, if we know that a set of data is considered to be normal, then we can use these facts to help us kind of interpret the data that we are given. All right, so let's look at this first one together. Here we suppose that the heights in inches of men from 20 to 29 years old in the US are normally distributed. and the mean is 69.3 inches, and the standard deviation is 2.92 inches. Find the following. So we want first the percent of men who are between 63.46 and 75.14 inches tall. So if we know, again, that the mean is at 69.3, we can start adding our standard deviation to the right or left. So if we do one standard deviation to the right, we get 72.22. And then if we go one standard deviation to the left, it's 66.38. And we can extend that out a little more because this doesn't quite encompass the numbers that we're looking for yet. So if you add a standard deviation again to the right, we actually end up at 75.14 and then 63.46 on the left. So this is within two standard deviations of our mean. So if you look at the data or the chart from our last page, we know that 95% of our data should fall within two standard deviations of our mean if the data is normally distributed. All right, so now let's look at this next one. This said, find the percent of men who are taller than 72.22%. Okay, so for this one, I brought in a little picture of the chart to help us. So we see that 72.22, again, is this value right here. So it's one standard deviation to the right. So it's kind of the cutoff being here. So essentially, if we want the percent of men who are taller than this, we're just going to add up everything above this line. So we want to find this right here. Let me actually shade it so it's a little easier to still see. So we want everything past that. So we're just going to add up those percentages. So we have 13.5% plus 2.35% plus 0.15%, and then that gives us 16% of our population. So you can see that we can use this normal distribution to kind of help us quickly find different percentages of the population that meet different characteristics. All right, so here I have one for you to try on your own, so please pause the video and give it a shot. All right, go ahead and check your work here. So here you can see we have the mean of 69.3, and then I just added multiples of our standard deviation to see kind of these different kind of breakdowns. And so from 60.54 to 78.06, that's within 3 standard deviations. So that's 99.7% of the population. And then shorter than 60.54, which was 3 standard deviations to the left, everything to the left of that is just 0.15% of the population. So now we're going to talk about something called a standard normal distribution and a z-score. So let's imagine, we have that last example where we have some mean value and we have our standard deviation, but what if we have a value that's not exactly 1 or 2 or 3 standard deviations above or below? Like what if it's somewhere in between, but you still want to calculate a percentage of a population? So to do that, we can use what's called a standard normal distribution. So standard normal distribution is a distribution where the mean is 0 and the standard deviation is just 1. So we can actually convert any type of data or any piece of data from a normal distribution to have what's called a standard. We can make it standardized and give it what's called a z-score. So then that would put it in reference to this standard normal distribution. So we could take any data point and we can give it a z-score by doing the data minus the mean, so the difference between your point and the mean, and divide it by the standard deviation, and that gives us our z-score. So then for our z-score, we can use what's called a standard normal table. So this, you can look at what your z-score is, and z-scores, there's z-score tables, like there's different ones. There's some that give you accuracy to the nearest hundredths or thousandths. This one just gives us to nearest hundredth. So for example, if you have a z-score of 1.3, on this column you would find the 1, and in this row you'd find 0.3. and you find the intersection. So a z-score of 1.3 gives you this value. So this value would tell you the area under the curve of your standard normal distribution up to the z-score of 1.3. So again, that would give you all of this shaded region here, which also would tell you the percentage of the population that goes up to the z-score of 1.3. So it would be about 90% of our population. So again, we can use the z-score to tell us the area of the curve up until that value, and then that tells us the percentage of the population up until that value. So even if something is not distributed in this way, by giving it a z-score, we can use the standard normal table and help us find a percentage of our population. So this is, again, really useful when we're looking for a range where it's not exactly 1 or 2 or 3 standard deviations from your mean. What if it's somewhere in between? And for this, you would be given a standard normal table. These are not things that I would expect you to memorize at all. So please don't worry about that. But you should memorize how to calculate a z-score. All right, so let's see if we can give one of these a try. So here we have the heights in inches of women from 20 to 29 years old in the U.S. are normally distributed. That is an important fact to know, with a mean of 64.1 and a standard deviation of 2.75. So they want the percent of women who are no more than 65 inches tall, so 65 inches or shorter. So if you notice, if you start at your mean and you add 2.75, 65 is somewhere in between, so that's not exactly a standard deviation away. So if you want to calculate this percentage, we're going to need to use our standard normal distribution. So first, we're going to need to give this data point a z-score. So we do 65 minus 64.1, so the difference between the point and the mean, and then you divide it by the standard deviation. You get about 0.3. So remember, on a standard normal curve, right, we assume that that center point here, the mean is 0, so if you have a z-score of 0.3, you're a little bit to the right of that. So if you use our standard normal table, let me put a picture in real quick. Here, if we look for the z-score, that's 0.3, I'll zoom in over here. So we do 0.3, so we do this row and this column. We see that it's this number right here. So this would be the area of the under the curve up until that point. So it's this area right here. So it's all of this area, which would represent the population up until this data point, which represents 65 inches tall. So this value, 0.6179, actually gives us that percentage. So it's actually 61.79% of the women are no more than 65 inches tall, 65 or shorter. Now let's try one where we're between two values. So it's between 60 and 63, so we need to get those individual z-scores, again, because 60 and 63 are not, exactly 1 or 2 or 3 standard deviations away from the mean, so we need to convert it. So we have 60 minus 64.1 divided by 2.75. So this z-score is negative 1.5. And then we have 63 minus 64.1 over 2.75. So this z-score is negative 0.4. So here, just to kind of visualize what's going on, when we find, so here's 0. So we have the z-score of negative 1.5, so I'll say it's like somewhere around here, and the z-score of negative 0.4 here. So we want to find this in between. So we want to find the area of underneath the curve in between those two. So to do that, I can find the area up until negative 0.4, which our table will tell us, and then I can subtract away this area, and that will give us the stuff that's in between. So let's look at our standard normal table now to find those areas. So for the z-score of negative 1.5, again, I do negative 1 and then 0.5, so it's right here. And then for negative 0.4, it's this value here. So the area under the curve from here to here is 0.3446, but the area under the curve from here to here, which is the negative 1.5, was this 0.0668. So again, to find the area in between, I will just simply do this minus this. So I'll do 0.3446 minus 0.0668, and we get 0.2778. So it gives us about 27.78% of the population. So again, sometimes we can just use the total area if it's like up until something, but if we want to find in between, we can find those individual areas and then subtract away the parts that we don't want. Okay, I have one last one for you to try on your own, so please pause the video and give it a shot. All right, go ahead and check your work here. So for part A, the z-score for this value is 0.7, so that gives you this value here. So that's the area under the curve up until 0.7. However, this says find the percent of women who are at least 66 inches tall. So it's actually, we want the stuff above that. So if you know the area under the curve up until this point, you can actually subtract that from 1, because it should all add up to 1, and then that will give you the area under the curve after that value. So you get about 0.242, so 24.2%. And then find the percent of women who are less than or equal to 61.6. So the z-score for that value is negative 0.9. So that gives you this value on your standard normal table. So that's the area under the curve up until that point. And since we want the women who are less than or equal to that height, that is the area we're looking for. So it's about 18.41%. All right, that is all for today's video. Thank you so much for watching.